Hey everyone, welcome to Math 481, Fall 2020. Unfortunately, it's virtual, but let's do our best to have fun. I really love this material. I love teaching this class, and so hopefully we'll all have fun together learning and talking about this material. So let's get started now. First thing, the material, the stuff that you learned in Math 248 or in some intro to abstract mathematics or transition to abstract mathematics, all of that material is fair game. You're going to need that material in this class. So stuff about functions, one-to-one, onto, relations, equivalence relations especially, cardinality, all of that stuff is going to come to bear in this class. So if you have questions or have forgotten some of that or need a refresher, this is the book that we're working with, right? It's this white one right here. I don't know how well you can see this, but it's the Abstract Algebra book by Fraley. In the first chapter, or I guess it's actually chapter, I don't think it's chapter 0. Chapter 0 gives you a quick review on sets and relations. And so if you ever have questions or can't remember what one of these things are, you can always review that material. You can always also ask me. I can't remember how equivalence relations work or something like that, and I can give you a quick refresher. So yeah, anytime if you have questions, come to office hours, right? I'm always willing to talk about this stuff and help you through it. Okay, so here we go. First thing, let's just review some standard notation. I'm sure that most of you have seen these symbols right here, but here we go. So I'm just going to write them down and then I'll remind you what these are. So what do we got? Natural numbers, integers, rational numbers, real numbers, complex numbers. You're not going to need to know a whole lot about the complex numbers, but you need to know what a complex number is and you need to know how to multiply complex numbers. And we will review and they will come up in this class. So even if you haven't had a course in complex analysis, that's okay. We will cover everything that you need to know about complex numbers in this class, but they will show up. Some other symbols, so let's see. I think your book uses this symbol right here, Z plus. This is the positive integers. Which is exactly the same. I tend to use this symbol right here for the natural numbers, and for me the natural numbers do not include 0. It's 1, 2, 3, 4, 5, and so on. So it's exactly the same as the symbol your book uses here, Z plus. Right? So Z plus and N are the same. So anytime in this book, if you see a little plus symbol, right, that means the positive half of the set. So Q plus, this means the positive rational numbers. Right, so then there, of course, there's also an R plus. What does R plus mean? Well, that's the same as then the interval from the open interval from 0 to infinity. The book also uses the symbol star, and so in general, now let's do it like this. So Z star. What this means is take the integers and remove 0. There's also Q star. That's going to be the rationals. Remove 0. So in general, and we'll use this notation, I'll just say etc. here. In general, star means take whatever set you're working with and remove 0 from it. Plus means just take the positive half. Okay, so our first definition, let's let S be a set. A function which we typically are going to use the symbol star as the name of the function. So instead of using a little f or a little g, in this case, for the function that we're about to define, we use the symbol star. So a function star from S cross S to S, right? This has a name, it's called a binary operation. So this is called a binary operation on capital S. So what is that saying then? A binary operation takes a couple of elements from S and assigns to that pair an element of S, right? That's what a binary operation does. So in fact, right. So very quickly now, typically now, if you're working with a function, don't write this down. I'm gonna change this. So what we would have, you take an ordered pair from S cross S, right? That's what elements of S cross S look like. And then if you apply the function to them, this right here then is the output. This output is going to be an element of S. This is really clunky notation, and so we're immediately going to redo that. So let me write it like this. If, say, S comma T is an element of S cross S, we typically denote the output of the function, so star st, by S star t. So instead of using function notation like this to denote the output, we're going to denote the output by S star t. So what does this happen? So here, just sort of commentary on this definition. A binary operation assigns to each ordered pair S comma T a unique element. And I should, just to emphasize, each ordered pair S comma T in S cross S. Sorry, I ran out of space there. Hopefully you can see this in the shot though. So it's each ordered pair ST in S cross S. To each such ordered pair, we assign a unique element S star T, and that's an element of S. So that's a binary operation. It takes ordered pairs from S cross S and assigns to it a unique element in capital S. Now, you've seen lots of examples of binary operations. So, for example, plus is a binary operation on Z, where plus is the usual operation of addition of integers. So how does addition work? Well, it takes an ordered pair M comma N and assigns to it the sum of those two. So for example, right, what do we have? 3 plus 4, right, we know is equal to 7. So how does this binary operation work? Well, it takes the ordered pair 3 and 4, 3 comma 4, and assigns a unique output, and that unique output is the sum, right? In this case, we know that's 7. Right, so this is also true for plus on Q, R, and C, right? So addition is a binary operation on the rational numbers, on the real numbers, on the complex numbers. Also true on the natural numbers, the positive rational numbers, positive real numbers, right? If you take two natural numbers and add them together, you get a natural number. That's a way of assigning to each pair that you want to add a unique output. So another example, plus is not a binary operation on z star. Remember, z star is a set of integers where you delete 0, right? So it's all integers except 0. And why is that? Well, because, so the reason, if you want to add minus 1 plus 1, what you get 0, but 0 is not in z star, right? So what we have is, right, if plus was going to be a binary operation, right? You don't need to write this down because it doesn't work, right? So if plus was a binary operation on z cross z, then what we would have is plus would be a function from z cross z, z star cross z star to z star, right? The problem is the codomain doesn't work in this case because to add minus 1 plus 1, we have 0. It would need to be in z star. So often we'll have a set S along with a binary operation, or along with an operation, so along with an operation, say star on S. Right, so think of an operation, including a binary operation. It's just a way to take a couple of elements from the set, put them together, do something, and give some new outputs, right? So to assign some output to each pair that we choose from here. So let's say that we have a set S along with some operation star on S. Now, to check whether star is a binary operation, on star, well, there's two things that we need to verify. So we must verify first thing, so for every little s and t in S, there is exactly one element assigned to say S comma t. In other words, you can say that this way, i.e. Star is well defined. So whatever formula you have for star, you need to make sure that it makes sense in the function setting, right? So that when you have an ordered pair S comma t, the output, which we would write as S star t, right, needs to correspond to exactly one element. And then the second part, so part 2, is that S star t needs to be an element of capital S. And so, yeah, right. And let me say this with some quantifiers. Let me say this a little bit better. So for every little s and t in capital S, S star t is an element of S. That is, we get the codomain correct. Right here is a place where it failed. Right? It satisfied part 1, right? The formula for addition always gives a single output, but in this bad case right here, the output didn't live in the appropriate codomain. So when there's, I'm writing this down partly because there's some terminology that goes along with this. So when part 2 is satisfied, so when 2 is satisfied, we say that that S is closed under star. Right, so when you have a situation where the operation, right, think of this operation on S as taking a couple of elements from S, combining them together and giving some output, as long when that output always lives in S, then we say that S is closed under our operation star. So in our previous example, Z star is not closed under addition. Right? Why is that? Because there exist elements in Z star, so that when you add them together, their output, their result, the resulting sum, is not in Z star. So let's look at some examples now, or some more examples. So let's let M of R be the set of all, let's do all matrices with entries in R. Okay, so take all possible matrices whose entries live in R. Matrix multiplication is not a binary operation on M R. Why is that? Well, because you can't take every pair of elements from here and multiply them together. They've got to have dimensions that work out so that when you multiply. So for example, if you took matrix A was a 3 by 5 and B was a 4 by 2, right? Then there is no way to multiply A times B, right? It's not defined, right? And so it fails part 1, right? Because here is a couple of elements that live in M of R, but there are no elements assigned to the ordered pair A comma B. And so it's not a binary operation. It fails part 1. Same for matrix addition. Right? Because you can come up with examples of matrices for which it doesn't make sense to add them together. They've got to have dimensions that match. Okay, next example. Let's say fix some natural number n, and let, so now we're going to use this notation, m sub little n of R. Right. This is going to be the set of n by n matrices with entries in R. So let this be the set of n by n matrices with entries in R. So now let's get precise, or let's be precise about this. So let's define the operation star on m sub n of R by A star B equals A times B. So I just want this to be the usual matrix multiplication. Now, since now that we're working with n by n matrices, multiplication works out no matter what. If you take two matrices here, since they're both n by n, you can multiply them. So since matrix multiplication is defined for all A and B in m sub n of R, star satisfies condition number 1, right? Since now let's think about what happens if you take A times B. If both of these are n by n matrices, then the result is an n by n matrix. And so since A, B is an element of M, N, R, star satisfies part 2. M, N, R is closed under matrix multiplication. That's how we would phrase it. And so what's our conclusion? Star is a binary operation. On M, N, R. So let's look at some more examples. So for our next example, let's let X be a set consisting of just the numbers 0 and 1. And what I want to do is define a binary operation on this set capital X. And so what I need to do is tell you how to perform this operation for each pair of elements from 0 and 1. Okay, I'm just looking, I know it looks weird, but I'm just checking the time, so we've been going for 23 minutes so far. Okay, so we're going to define star on X by, so let's see, I want to tell you how to do 0 star 0, and that's going to be 0. 0 star 1 is going to be 1. 1 star 0 equals 1. And 1 star 1 equals 0. So this, since there's only a finite number of possible pairs, I can tell you how star behaves, not by formula, but by just listing all possible outputs. Right? So now what we have is, so star is a binary operation on capital X. Why is that? So what is part 1 of the condition? Well, we need to have it defined for every possible ordered pair. And so there are 4 ordered pairs living in X cross X, 0, 0, 0, 1, 1, 0, and 1, 1. So we have it defined for all possible. And then what's condition 2 to be closed, we need the output to always live in capital X, and it certainly does because our outputs are either 0 or 1. Right, so that tells us we've got a binary operation on X. Now, in certain cases, it's nice to write down the binary operation or describe how the binary operation works by means of a table. So, say it like this, it is sometimes convenient to describe, or I guess I want to say define actually, so to define the binary operation star on the set capital S by means of a table. And so here's the way we do this. So this only works if we have a finite set. So if, let's say, S equals the set consisting of the elements S1, S2, dot, 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 all the way up to Sn, we list the elements in order along the top row and left-hand column. So let me draw the picture of what I'm saying here. So I'm going to draw my table like this. So this is a diagram that's going to tell us how a particular binary operation works. Oh, I kind of put too many here. So what we would do in that upper left-hand corner, I'll put star. That's the name of our binary operation. And so now along the top row, I'm going to list the elements S1, S2, S3, S4, S5, dot, dot, dot. If there's 27 elements, then I'm going to have 27 columns. So eventually I'll get to the very last one, which is going to be S sub n. Do the same thing along the left-hand side. So I've got an S1, an S2, S3, dot, dot, dot. Eventually I get to S sub n. Okay, so now in our boxes, what we're going to do is let me write out the actual, well, let me say it in words first. So S sub I star S sub j is listed in the column, let's say it this way, listed in the entry or the position corresponding to S sub i's row and S sub j's column. So for example, okay, so right here then we would put S1 star S1. Right here we would put S1 star S2, S1 star S3, and so on, all the way down till we get to S1 star S sub n. So then here we would put S2 star S1. Here is S2 star S2. This would be S3 star S1. And so in general, in the ith row, or the S sub ith row, and the S sub jth column, we would write the element S sub I star S sub j. Okay, so there's the idea. Now, I want to first do it using, so we did this, we defined this binary operation on x, and the way we did it is just wrote it all out, right? Sort of brute forced it. But what we can do instead is define this exact same binary operation on capital X by means of a table. So it's called star, so let's put a star there. The elements are 0 and 1. 0 and 1. Okay, so now who is 0 star 0? It's 0. Who is 0 star 1? It's 1. Who is 1 star 0? It's also 1. And then who is 1 star 1? 0. Okay. So there is the table corresponding that exactly defines this binary operation. Right? So sometimes it's nice to just list it all in tabular form. Okay, so next example, let's let capital X be the set 0, 1, 2. Now I want to define, so let's define star on X by A star B is equal to, and I want to do addition mod 3, so it'll be A plus B mod 3. So hopefully everybody's seen modular arithmetic either in number theory or in math 2. You probably saw it in math 248, again probably in number theory. So how does this work, right? A plus B mod 3, that's going to be the unique remainder that you get when you run the division algorithm on A plus B. When you divide it by 3, who's the remainder? So what I want to do, first we can just kind of, let's say some words here. So since A star B is uniquely defined for each pair A comma B in X, we see that star is a binary operation on capital X. So what we can do is we can actually make the table now for this binary operation. And so what this table does, it sort of displays how the arithmetic on the set behaves. So in this case now, we're going to have 3 elements. So we're still calling it star, but now our elements are 0, 1, and 2, 0, 1, 2. Okay, so now I need to fill in these blanks based on how our arithmetic works here. So 0 plus 0, or 0 star 0 is 0. 0 star 1 is 1, and then we get a 2. 1 star 0 is 1. 1 star 1 is 2. 1 star 2 is 0. 2 star 0 is 2. 2 star 1 is 0. 2 star 2 is 1. Right, so there's the table corresponding to this binary operation that's given by the familiar formula of arithmetic mod 3, addition mod 3, I guess I should say. So let's see. So another example. Oh no, sorry, I'm going to do definition now. Sorry, I spaced out for a second. Okay, so let's see. Let star be a binary operation on capital S. So then star is, and there's two parts to this definition. So part A, star is commutative. If A star B is equal to B star A for all A and B in capital S, right? So there's your typical definition. You've I'm sure heard the words commutative in the past when it comes to operations like addition and multiplication and so on, right? Now what we're doing is generalizing this idea, right? We're saying that it's commutative if, right, you can do the operation in either order and you get the same output, the same result. There's also associative. So part B, it's associative if A star B in parentheses star C is equal to A star B star C for all A, B, and C in capital S. Right. So two familiar definitions, right? You've seen both of these words before. Now we're generalizing it. I think you've seen it mostly in the context of addition of integers and rational numbers and real numbers and so on. Multiplication also, right? Now what we can do is generalize these terms, right, to an arbitrary binary operation. So let's look at this example. Let's let S be the set of all functions, and we want functions whose domain and codomain are the natural numbers. So all functions that go from the natural numbers to the natural numbers. So for example, so here's an example of a function. The formula f of n equals n plus 1, right? The input is a natural number, the output is a natural number. So this function f right here is one element inside capital S, right? And there are a huge, this is a very, very large set, right? This is an infinite set. You can think about whether it's countable or uncountable. Right? It's a very large set, though. Lots of functions in here. Now, the operation, and let's use the usual symbol, circle of composition is a binary operation on capital S. So you can check then composition of two functions living in S gives you a function that's also an S. So what do I say? You can check, so let's just say it like this. So as an exercise, check. Circle is associative in fact, if you're in my Math 248 and probably any Math 248 class, we show that composition of functions in general, right, is an associative operation. So composition of functions is associative, but you should easily be able to come up with an example. So we can say, but composition is not commutative. All right, so to verify this, you should come up with an example, two functions from n to n, so that when you do the composition in one direction and the other direction, you get two different functions. Another example, so matrix multiplication on m sub n r is associative. That's one of those properties of matrix multiplication. So it's associative, but of course we know that matrix multiplication is not commutative, but is associative, but is not commutative. Now let's end with this definition here. So a pair so it'll be S comma star, where S is a set and star is a binary operation on star, is called, so this is a binary structure. So what we have, this ordered pair notation, we're not going to be that heavy on it, but occasionally you want to think in this way, right? So a binary structure is a set together with a binary operation on that set. Oops, oh, and right there, sorry, I screwed up that. That should say a binary operation on S. So a pair like this, where S is a set and star is a binary operation on set, we call that a binary structure. Now, let's end on this note. Abstract algebra, if you want to know what we're going to study in this course and in 482 and in 483, and in general when you study abstract algebra in a nutshell is the study of binary structures. So we'll say it like this, abstract algebra is at its heart, so abstract algebra is the study of binary structures. So if we don't want to just study sets in abstract algebra, what we're studying is sets together with ways to take elements of the set, combine them together, and give an output. You've seen this many, many times when you're doing arithmetic. What do? You add two integers, you get an integer. You multiply two real numbers, you get a real number, right? Those are both examples of binary structures, right? R together with the usual notion of multiplication. It's a binary structure. Z together with plus, the binary structure. And so that's what we're doing in abstract algebra. We're generalizing the familiar notions of arithmetic that you've learned since first grade, how to add numbers, how to multiply numbers, and so on. Right? We're generalizing these into more arbitrary abstract settings. Right? So in general, if you have a set and a binary operation, that's going to be what we're interested in when it comes to abstract algebra. Okay, so we'll see you next time.